Hi, in this video, I'm going to talk about more example of vector spaces. Okay, if you remember in the last video, we talked about this R2. Okay, so I will just show you that how is the addition and scalar multiplication acting there, and then we will talk about more examples. So let's get started. Okay, so in R2, the addition is acting like this. Let's say this is one and this is another element. So this is our addition: 1 plus 2, 3, 2 plus 3, 5. And how is the scalar, that dot thing, working? This is acting like this. Let's say 2 and dot, let's say this element. Then this is 4 and this is 2 into 3, 6. So as you can see, this one. Okay, this this is our dot. Okay, now I already verified how the 8 axioms are holding true. Now let's go to something called example number 2, which is example vector space is polynomial. Example 2 is our polynomials. Okay, so what are polynomials? Let's be precise and say let's polynomial over R. So this is something like this. You take a n x n plus a n minus 1 x n minus 1 a n minus 2 x n minus 2, something like this. Okay, so where this ai is r from r and x is a variable. Okay, now some example will be like this. Let's say 2x cube plus 3x square plus 4, or let's say x cube plus 2, or let's say x4 plus 5x plus 2. These are examples. Okay, now how do we form a vector space? What will we take as our addition? So let's say this is my first, let's say an xn and so on, a1x plus a0. This is my first polynomial, and this is, let's say, my second polynomial. Then if you add, you will get an plus bn xn a1 plus b1. You add coordinate wise. Okay, right? You add the power of xn together, you add the power of xn minus 1 together, and so on, so forth. Okay, so let's see how that, let's say I add this one and this one. So this plus this. Okay, uh, this. So how is the addition going to work? This is like you add this and this is 1. Okay, so 3 x cube with total, and x square is only 3, this thing, and x we have no x, so that will be 0x, and then 4 plus 2, so it will be 6. So 3x cube plus 3x square plus 6. So this is what we will get. Okay, so now we also need to define a dot, right? So how do we define a dot? Let's say there is, what is dot, like dot, this dot operation takes r, and then v is our polynomial, and it will give back a polynomial. Okay, so I'm defining it like this. Let's say 3 dot any vector polynomial like this, then it will give back, let's take a general c, and it will give me c a n x n, the c a n minus 1 x n minus 1 plus c a2 x2 plus c a1 x plus c a0. Done. So now how do we okay, so let me show an example. Let's say 2 into this thing. So this will be 2x cubed plus 4x minus 8. So now we have defined a dot and we have defined also an addition. Okay, this one is our addition. Okay, this is our definition of addition, and this is our definition of this dot product. Okay, now you verify this 8 operation 1, 2, 3, 4, 5, 6, 7, 8. Okay, and you will see that these 8 axioms are true. So this is this polynomial over R is a vector space, and we denote it by P and R. Okay, where n is the degree. Okay, what is degree of a polynomial? This is just degree of a polynomial is just the highest. Let's say this is my polynomial, and this is the degree, the highest power of x whose coefficient is non-zero. Okay, so let's say we have 5x5 plus 3x square minus 1. Then this degree is 5, because this is the highest power of x. Okay, uh, so here we are taking all polynomials. You can also do something like check that polynomial whose degree is 3 union 0 is also a vector space. This will come later. I will prove this later if required. But yeah, there is nothing special about 3. You can take it any n. Okay. Now let's move to a different example. Example number 3. So okay. So in this example, I'm going to consider the vector space, what is denoted by M and R, where M and R denotes matrix of size n cross n with coefficient in R. Okay. So uh, okay, let's see. What do I mean by size? Size means the rows and columns. Okay, in this matrix. And how do I define this addition? I'm defining like this. Let's say this one is one matrix of size 3 cross 3. And this one is another matrix. and you can see what I have defined. I am defining it to be adding like this. Okay. Okay, so I don't have a space, but you got the feeling, right? So let's take an example. Let's say vector space M3R. So you have three, let's say 2.5, 2, 1, 4, 6, 8, 9, minus 10, plus let's say another matrix 2.2, 1.1, 5, 7, 8, 9, 1, 2, 3. So I am defining the addition 3 plus 2.2. This first entries would be 5.2. Now 2.5 plus 1.1, 3.6. 2 plus 5, 7. Okay, 1, 7, 8. 4, 8, this will be 12. 6, 9, 15. Okay, 8, 1, 9. And 9, 2, 11. Minus 10 plus 3, this is minus 7. So now next is I need to define also this dot product. Okay, how do I define it? Like 3 into not 3, let's say C, an arbitrary real number. And how do I define it? Define it like this: CA11, CA12, CA13, CA21, CA22, CA23, CA31, CA32, CA33. Okay, so this is the matrix dot. Okay, so for an example, let's say 2, 3, 4, 2 dot 6, 7, 8, 9, 10. So this will be 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so all right. Okay, so now you check the 8 axiom that I like described in the starting lecture. So you will see that M3R is a vector space. Okay, you check this. Okay, in this case, our zero vector will be this one, and let's say a some is matrix. Let's say A11, A12, A13, A21, A22, A23, A31, A32, A33. This its inverse is this one, minus A11, minus A12, additive inverse. Okay, A21 minus A22 minus A23 minus A31 minus A32 minus A33. So this is example 3. You check the other examples. Okay.